Let's look at a result about the Riemann integral that'll make it a little bit stronger. We're going to suppose that f of x is non-negative and continuous on a closed-bounded set AB. If there exists an x sub 0 in the open set AB such that f of x sub 0 is positive, then that would imply that the Riemann integral there is also positive. So what we want to do is utilize some of the aspects of continuity, namely preservation of sign. So what we had back at the beginning of the course is that if we have a continuous function on a set and we have an actual value of the function that's positive, then that positive sign has to spread over an interval of content. So for instance here, with the x sub 0, f of that number being positive, we would expect the positive sign to spread over an interval about x sub 0. So what I've written here is basically the arithmetic. So there exists a positive delta such that if x lives in the interval x sub 0 minus delta to x sub 0 plus delta, this interval right here, which is in AB, this will imply that f of x is indeed positive there. Again, preservation of sign. Now to move the proof forward, what we want to do is make this interval a little bit smaller and create a closed bounded set. So what I'm going to do is set CD to be the closed set x sub 0 minus delta over 2 to x sub 0 plus delta over 2. So we're just going to bring the closed set inside a little. So basically we'll have something like this. So now what we want to use is the continuity to give us the Riemann integral. So we know continuous functions are Riemann integrable. So we've got that. And then a very popular result called additivity will now allow us to break up the interval from A to B. So what we're going to do is go from A to C, C to D, and D back to B, and break up the integral in 3 pieces. So we have the integral here of f, a to c, the integral here of f, c to d, and the integral here of f, d to b. Now, we know the non-negativity of f will ensure that the first integral is non-negative, and also that the third integral is non-negative. But what's the case about the middle integral? Does it actually improve? And I think we can show that it does. By EBT, that is, this is a closed bounded set, we will let this positive number m be the minimum of f there. Then, using a result from the Riemann integral, we can now say that m times the length of the integral d minus c is actually a lower bound for the Riemann integral. And also, by EBT, the corresponding maximum times the length of the interval, just to add this, is an upper bound. We don't need that for this result, but this is good for your notes. But this is a positive quantity. So indeed, the Riemann integral over CD is a positive real number. And so that tips the balance in our favor. So this portion here is strictly positive, so this will imply that the integral from A to B is therefore positive, which is what we wanted to prove, and we are done.